Hello class, in this section we're only going to define average power, which is work over time, and the unit for power is watts. Our first example, we have a 60 kilogram jogger that runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters, and we want to estimate the jogger's power output in watts and horsepower. We start off with our new equation. However, we don't know what work is. Like a previous example, when we're referring to the object, and in this case the jogger's power, they're really referring to the normal force. So we need to find the work done by the normal force. And just like that previous example, the work done by the normal force ends up equaling mgh. Now we can plug in our power equation, plug in chug, and we get 660 watts for the jogger's output. And then to figure out the horsepower, all we need to do is use a unit conversion, which is 1 horsepower equals 746 watts. And so we get an answer of 0.88 horsepower. Now power can also be rewritten down as force times velocity, because we know that work equals force times displacement, and displacement over time is the definition of velocity. Alright, let's do an example. We want to calculate the power required for a 1400 kilogram car under the following circumstances. Assume the average retarding force on the car is 700 newtons throughout. The car climbs a 10-degree hill at a steady rate of 80 kilometers per hour for part A. We'll start with our new equation, power equals force times velocity. However, we need to find the force of the car's output. To find this, we'll use Newton's second law. Sum of the forces in the x direction equals 0 because it's moving at a constant velocity up the ramp. Now notice that the coordinate system is angled with the ramp. Write down all your forces along the x direction, along the ramp, and notice that the weight component along the ramp is mg sine of 10 degrees. We want to solve for F, which is the car's output force. Now we can plug in chug to actually find the value of the car's output force, which is 3100 newtons. Once we have that, we can just plug in chug to find the car's power, which is 6.8 times 10 to the 4th watts. Or I can just say 68 kilowatts, and in case you're curious, it's 91 horsepower. Now for part B, the car is on a level road. And we don't know the car's force output, but we are given some information about velocity and time. From there, we can figure out what the car's acceleration is just by using delta V over time. Plug in chug, and that gives us 0.93 meters per second squared. This is important to know because when we use Newton's second law to find the car's output force, it doesn't equal 0 because the car is accelerating. Plug in all the forces along the x direction for the car on the flat road, which is just the car's force output and friction, or the retarding force. We solve for the car's force output. Plug in chug, and we get 2000 newtons. Now we can plug in chug to get the car's power output, which is 6.1 times 10 to the 4th watts, or 61 kilowatts, or in case you're curious, 82 horsepower.